Today we are going to talk about voltDB. Here is a quick info about voltDB. Important thing to note here is it's written in C++ and Java, and it embeds EdStore and HyperSQL. voltDB is a fast in-memory relational database system for high throughput operational applications acquiring orders of magnitude better performance than a conventional RDBMS. It's almost 100 times faster. SQL as the native data language, simplifying development and enabling richer interaction. ACID transactions to ensure data consistency, integrity, and always accurate results. Built-in high availability and fault tolerance, and then cross data center replication for high availability and disaster recovery in geographically distributed clusters. Geospatial query support for location-based apps. voltDB's massively parallel architecture also provides elastic scalability running on low-cost commodity servers. It allows application developers to scale applications simply by adding servers to a voltDB cluster instead of building complex, costly sharding layers. voltDB's ACID compliance ensures developers never need to sacrifice data consistency to gain high performance or scalability. voltDB leverages the following architectural elements to achieve its high performance, scaling, and high availability objectives. First, automatic partitioning across a shared nothing server cluster. Second, main memory data architecture. Third, elimination of multi-threading and locking overhead. Fourth, clustering of high availability and active-active replication for disaster recovery. Then ad hoc SQL access via JDBC and client language bindings, multi-statement transactions via stored procedures, in-database machine learning-driven smart streaming, cloud-native container-based application deployment with Kubernetes, and native exports to OLAP data warehousing and Hadoop data lakes. voltDB eliminates traditional Dbmss overheads while preserving ACID, unlike NoSQL. With voltDB, data and processing associated with it are partitioned together and distributed across CPU cores in a shared nothing hardware cluster. Data is held in memory for maximum throughput to eliminate the need for buffer management. Each single-threaded partition operates autonomously, eliminating the need for locking and latching. Data is automatically replicated for intra- and inter-cluster high availability and disaster recovery. Analytics is done close to the data for complex, low-latency real-time decisions. Now, why do traditional DBMSs have difficult scaling? The diagram here gives a good picture of it, where around 10% of the time is done for useful work and rest 90% are spent in index management, logging, latching, locking, and buffer management. So let's look at each of them. So first, the index management. B-tree, hash, and other indexing schemes require significant CPU and I/O. Write-ahead logging. Traditional databases write everything twice, once to the database and once to the log. Moreover, the log must be forced to disk to guarantee transaction durability. Logging is therefore an expensive operation. Third, locking. Before touching a record, a transaction must set a lock on it in the lock table. This is an overhead-intensive operation. Fourth, latching. Updates to shared data structure like B-tree, the lock table, the resource table, etc. must be done carefully in multi-threaded environment. Typically, this is done with short duration latches, which are another considerable source of overhead. And fifth, buffer management. Data in traditional systems is stored on fixed-size disk pages. A buffer pool manages which set of disk pages is cached in memory at any given time. Moreover, records must be located on pages and the field boundaries identified. Let's look at the history of voltDB. voltDB originated from EdStore, a research project from Brown University and MIT under Michael Stonebraker, Simon Madden, and Andy Pavlov. In 2009, it started as a spin-off in Boston. Checkpoints. voltDB offers non-blocking and blocking checkpoints. The snapshot created could either block all other transactions or be done in a non-blocking way, that is, copy on write way. voltDB uses deterministic concurrency control. voltDB schedules transactions deterministically on each partition of the data in the cluster. For transactions that span across partitions, a global serial order controller is responsible for determining the execution order. MVCC mode is only used when taking snapshots. voltDB is based on the standard relational model. A relational model represents the database as a collection of relations. A relation is nothing but a table of values. Every row in the table represents a collection of related data values. These rows in tables denote a real-world entity or relationship. Apart from the default tree index, voltDB also supports hash index. voltDB supports serializable isolation level with ACID guarantee. The deterministic ordering of transactions is achieved by controllers at each data partition. There are 4 levels of isolations in general. First is read uncommitted. Transactions are not isolated from each other in this isolation level. If the Dbmss supports other transaction isolation levels, it ignores whatever mechanism it uses to implement those levels so that they do not adversely affect the other transactions. Transactions running at the read uncommitted level are usually read-only. Then there is read committed. The transaction waits until rows write-locked by other transactions are unlocked. This prevents it from reading any dirty data. The transaction holds read lock or write lock on the current row to prevent other transactions from updating or deleting it. The transaction releases read locks when it moves off the current row. It holds write locks until it is committed or rolled back. The third one is a repeatable tree. The transaction waits until rows write locked by other transactions are unlocked. This prevents it from reading any dirty data. The transaction holds read locks on all rows it returns to the application and write locks on all rows it inserts, updates, and deletes. For example, if the transaction includes the SQL statement like select asterisk from orders, the transaction read locks rows as the application fetches them. If the transaction includes SQL statement like delete from orders where status equal to closed, the transaction write locks rows as it deletes them. Because other transactions cannot update or delete these rows, the current transaction avoids any non-repeatable reads. The transaction releases its locks when it is committed or rolled back. And then finally we have serializable isolation level. Here the transaction waits until rows write locked by other transactions are unlocked. This prevents it from reading any dirty data. The transaction holds a read lock or write lock on the ranges of rows it affects. For example, if the transaction includes a SQL statement like select asterisk from orders, the range is the entire orders table. The transaction read locks the table and does not allow any new rows to be inserted into it. If the transaction includes SQL statement like delete from orders where status equal to closed, the range is all rows with the status of closed. The transaction write locks all rows in the orders table with the status of closed and does not allow any rows to be inserted or updated such that the resulting row has a status of closed. Because other transactions cannot update or delete the rows in the range, the current transaction avoids any non-repeatable reads. Because other transactions cannot insert any row in the range, the current transaction avoids any problem, any phantoms. The transaction releases its lock when it is committed or rolled back. Now you might wonder, what is the difference between repeatable read and serializable? In a repeatable read isolation level, new rows can be inserted into the dataset. In serializable isolation levels, all the rows are locked for the duration of the transaction. No insert, update, or delete is allowed. Now let's talk about logging. voltDB supports transaction level logging for all the stored procedures that are invoked. Now, by command logging, the amount of memory overhead is minimized since a single stored procedure invocation could contain arbitrary number of SQL statements. Only logs after the latest snapshot are kept, and the logs are flushed to the disk at regular interval. This feature is only available in the Enterprise Edition. Now, voltDB uses stored procedure query compilation. Now, stored procedure is nothing but a pre-compiled SQL statement. This means that once we have compiled a query, it stores the result, and the next time we don't need to compile it again and again. It means it is prepared SQL code that you can save and reuse multiple times. voltDB uses materialized query execution model. Here each operator processes its input all at once and then emits its output all at once. The output can either be whole tuples or subset of columns. It's better for OLTP workloads because queries only access a small number of tuples at a time, which leads to lower execution and coordination overhead and fewer function calls. It's not good for OLAP queries with large intermediate results. MongoDB is another example which uses materialized model. voltDB uses SQL and stored procedure as its query interface. voltDB also allows the user to define precompiled stored procedures. voltDB is designed to be an in-memory relational Dbmss. Its data persistence is achieved by snapshots stored on disk. voltDB is only designed for the fast OLTP queries. The stored procedure in voltDB allows the users to define a transaction once and to be invoked later with given parameters. Stored procedures precompiled to reduce execution time. Temporary queries are automatically compiled and executed as a stored procedure. voltDB supports stored procedures written in SQL or Java. voltDB runs on a sharded Dbmss cluster. Data partitioning and replication is done automatically across the cluster. Views in voltDB are materialized to improve read speed, and all updates to the original table will have a performance impact. A materialized view is a database object that contains the results of the query. For example, it may be a local copy of data located remotely, or maybe a subset of the rows or columns of a table on joint result, or maybe a SUMD using an aggregate function. Now here are some good voltDB alternatives. The top few are MongoDB, Google Cloud SQL, Oracle Database, Amazon Aurora, Redis Enterprise Cloud, Single Store, and Neo4j. Here is an overall customer advice. For startups in various stages of their funding, probably they can avoid using voltDB. They should use something cheaper and something which folks have used for years like MySQL, since it will be the easy skill set to find. Use voltDB only if you have very specific need or cash to come. For mid-sized to big companies, yeah, for sure, you folks have a ton of cash, so give voltDB a shot. Here are some good references if you want to learn more. That's all I had for voltDB. If you have questions or suggestions, then subscribe and leave a comment.